Okay, so we have here an old exam question, not that old. This is an exam question from last term. This is from fall 2020. Do recall that in that term, the exam questions were deliberately written to be more thought-provoking, more sort of problem-solving oriented than most in compensation at the time for the extra resources that students had in terms of extra time to work on the exam and open notes, open book, etc. So this is a challenging question. But anyway, I want to walk through the solutions. I think it's a really nice exercise, and it has some nice nice bits in it, nice bits of creative thinking that come up. So here we go. Sharing screen. All right. So what we are looking at here is number 5 from, again, fall 2020. So what we've got is a line going through the origin. We want to talk about rotating a quarter turn counterclockwise around that line. Now, y'all have seen in the past questions where we rotate around a line, and the big idea is you look at, well, what happens to the standard basis vectors, and those are the columns of our matrix, and it's end of story, right? And it's pretty straightforward. All linear transformations, if you know the images of the standard basis vectors, those are your columns. Great. The problem here is that we are looking at a line that is particularly inconvenient. This is not a coordinate axis. This is not one of those sort of 45-degree lines or something like that that has nice symmetries where the geometry just very easily tells you exactly where the standard basis vectors go. No such luck. Okay, so what we're going to do here is make use of a different basis first. And once we understand this linear transformation with respect to a different basis, then we'll talk about a change of basis to get it in terms of the standard basis that we're interested in. And ultimately, we're looking for this matrix that does this all with respect to the standard basis. Notice no mention of bases. Well, no mention of bases in the statement of the question. So we assume everything should be assumed to be in terms of the standard basis. So these are all coordinates with respect to the standard basis. Okay. Yeah, so first observation, we look at hint number 1, and it suggests these two vectors that might help. That's code for these are going to be really useful. The question would have been too hard without these being given. So there we go. And now what we do with them is up to us, though. Seems, though, like a natural choice. In fact, the hint even says might form a convenient basis. So let's do that. Let's take these 3 vectors, v1, v2, and v3, make a basis out of them. Conveniently, let's notice that they're all perpendicular to each other. Well, that's nice. A couple easy dot products confirms that. They all have magnitude 3. Cool, right? Might be useful at some point. Okay, so the temptation then is to argue as follows. The temptation is to say, well, this first vector is like this. By the way, you'll notice I've drawn it pointing up. Do notice that its third coordinate is positive, right? So it is, in fact, some way, somehow pointing up-ish, and that'll be relevant in a moment. And then now we've got these other 2 vectors given. Let's see here. So v1 is that one. These other 2 vectors, v2, I'm going to draw like, let's say like that. And then v3, I'm going to draw, let's say like that. And again, we've noticed that everything's perpendicular to everything else. And there is a temptation then to say, well, as we rotate around this line there, that's our line L, that you can just see exactly what happens in that rotation. That, well, looks like V2 rotates into V3, so it seems, right? And then V3 rotates around, or you can probably see without too much trouble, into negative V2. Doesn't that seem plausible? And this is actually pretty close to reality of this circumstance, but it does this ignores a fundamental worry about geometry in 3 dimensions. And this is something that every students always need to be head on a swivel, kind of thinking about, and that is this ignores handedness. There are 2 handedness possibilities, and in in drawing these vectors, I was somewhat careful about which direction V1 points, but I just kind of arbitrarily labeled V2 and V3 as being kind of like that. And how do I know that they are, in fact, as listed like this? In fact, as I have it drawn, you see it's sort of a right-hand order, right? So V1, well, let's see here. I guess it'll look like V1, V2, V3 from the point of view of this camera. How do I know it's like that? Maybe V1, V2, V3 is left-handed order. We can't just assume, right? So how do we resolve this? Well, before we get ahead of ourselves and assume what rotations are like this, let's decide, is this the right way or the wrong way? And a couple different ways you could do that. You could take this trio of vectors and make a matrix and take the determinant. Another thing you could do is take 2 of these vectors and take their cross product and see if it becomes what you expect. And that is what gives it away, actually. So I take V2 and V3 and I cross them, and I notice that I get a vector that's in the negative of the direction of V1. So V2 cross V3 points down. And well, that means that, and again, you have to play the game with your hands. V2, V3 crossing pointing up would be like that, but it's not, it's down. So my assumption over here that V2 was like that and that V3 was like this, nope. This would have the cross product pointing up, which it doesn't. Right, the cross product points down, and so I can't have V2 there. That one's V3, and V2 is down here. Okay, and so again, with V2 cross V3 then pointing downward, as indicated there. Okay, so that's it's a little subtlety, right? A lot of students kind of weren't appropriately worried about this orientation issue. And again, whenever you're in 3 dimensions, be on the lookout for where in your argument or in your pictures you might inadvertently be accidentally assuming something about handedness. Okay, so that being noted, let's see here. We have this basis, and the rotation picture is still just as easy as we thought it was going to be. It's just a little bit different. Instead of V2 rotating to V3, V3 rotates into V2. And instead of V3 rotating to negative V2, we have V2 rotating to negative V3. Right, so no big deal. And then, of course, V1, around the line that it is parallel to, V1 rotates into V1. Okay. All right, so the geometry gives us this picture, and that allows us to immediately write down what this rotation matrix is. Wait a minute, with respect to this basis, right? So in the language of this carefully chosen basis of vectors V1, V2, V3, we can write that down. Do remember that the process there is whatever input basis we have, those are what we put in to the linear transformation, and then we look at the outputs and we write those outputs in the language of that output basis. Okay, and of course, these equations up here are exactly that, right? Here's me putting the V1, V2, V3 into the rotation transformation, and then what comes out are, well, I have these coefficients here, and this is 1 V1 plus 0 V2 plus 0 V3, so thus 1, 0, 0. And then likewise, this is 0 V1 plus 0 V2 plus negative 1 V3, etc. Okay. All righty. So now we have found a matrix. Of course, this is not the matrix we were interested in, right? We were interested implicitly. I mean, the question was stated in terms of the standard basis. So we're looking for the matrix with respect to the standard, with respect to the standard basis. I know instead the matrix with respect to this different basis. So we just have to do a change of basis. And at this point, it's mostly just a kind of standard algebra. There's one little tricky move that we'll deal with. First, let's find the change of basis matrix itself. Change of basis from alpha to S. I would need to find the coordinates of the alpha vectors with respect to the standard basis. Oh, well, conveniently, those were given, right? That's what I chose here. That's this basis that I chose, V1, V2, V3, all given with respect to the standard basis. No other basis indicated. We assume the standard basis. We infer the standard basis. So yeah, so that's just those columns. Well, blue. That's these columns here. And that part's very straightforward. To find the other change of basis, to the change of basis back, right? How do we convert back? We need to invert the change of basis matrix that we just found. And here's where we're going to use hint number 2. Go back up here to hint number 2. If the columns are all perpendicular, then, which is interesting. Why would how would that be? But the product with its transpose is diagonal. That's the big hint. Now let's notice we already observed that these basis vectors are perpendicular. So having made them our columns here, indeed we have a matrix whose columns are all perpendicular to each other. So let's write down what we have from the hint. The hint, again, we're going to assume that the instructor, that's me, when writing this question, didn't deliberately give you any red herrings to take you off in a bad direction. So somehow it's presumably going to be useful to observe that this matrix, when multiplied by its transpose, will give a diagonal matrix. Right, so the product with its transpose is diagonal. We write that down. Here it is. So the matrix with the orthogonal columns multiplied by its transpose, those columns become these rows, right? That's how you transpose. And it's diagonal as promised, right? Now, this is a matter of kind of multiplying these things out. But you multiply this product and you get this diagonal as promised. Now, a little bit of foreshadowing, because we are going to talk about this later in the course. Why does this happen? Is this a coincidence? How could that be? It's actually not that surprising if you think about it. I mean, how do we compute, for example, this, how do we compute, let's say, this element, right? Where does that come from? Well, we do a dot product of the corresponding row with the corresponding column. But wait a minute, don't forget let's see. Well, gosh, I wish I'd done this backwards. This row is this column. And so what we effectively have is a dot product of 2 of the columns of this matrix. And orthogonality kicks in here, and I wish I had written these in the other order, but there's going to be an argument along these lines that the punchline of which is that, well, of course, these zeros are immediate consequences of the fact that these columns are orthogonal. It's going to turn out as well that these columns are orthogonal too. Yeah, anyway. Okay, that's just a side note. But this arithmetic tells us what diagonal product. Now, why do we care about that? Well, keep in mind, we're looking for the inverse. We're looking for the inverse of this matrix here. And I see something I can multiply it by to give me 9 times the identity. So we just divide by 9 here on both sides of the equation. dividing by 9 on both sides of the equation, I get, in fact, then a matrix that when I multiply it by the matrix I started with, I get the identity. And so that means that this purple matrix is the inverse matrix. So that's very convenient. Nice little trick. Okay, and at this point, it's all over but the arithmetic. Here's our strategy for how to do a change of basis. If you know the matrix with respect to one basis, and you want to find the matrix with respect to a different basis, which by the way is what we were asked, was to find the matrix for that rotation. No discussion of bases given, therefore assumed, inferred that we're looking for with respect to the standard basis. All we do is conjugate appropriately, and specifically, we start with standard basis language. If I convert into alpha language and then do the rotation in alpha language and then take that result in alpha language and convert that back to standard basis language, then the punchline is I have done the rotation. I did it in a sort of a more convenient form by doing it with respect to this other basis, but I have done the rotation where standard basis input and then a standard basis as the output. Okay. So there's that conjugation, just like in the lecture. And we know all these matrices, right? That came from the geometry argument. This came from PAT formula for how to find a change of basis matrix. This came from our clever argument about orthogonal columns, matrices with orthogonal columns, and plug and chug, and out comes the matrix we wanted. So I think this is a really interesting problem. It underscores the fact that very often a question that we're interested in is just not naturally suited to be analyzed with respect to the standard basis. We might need to understand it with respect to the standard basis, but it might not be naturally set up for so. And yet it might be beautifully set up to understand with respect to some different basis, right? Where we can instantly write down, oh, well, very easy observations about what this transformation does to those vectors. So this really underscores the value and the power of the idea of change of basis for linear transformations. Okay, so I hope this has been a useful discussion. And let's see here, I will stop the recording.